So when we curve sketch, we first of all analyze f. We look at the domain, the intercepts, the symmetry. We look to see if there's periodicity. Also, there could be vertical asymptotes or horizontal asymptotes. Then we look at f prime, and initially we try to find the critical numbers. And critical numbers are where f prime is equal to 0 or where f prime does not exist. After doing that, we look for intervals of increase and decrease. Then we look at f double prime. Again, we look at points where perhaps f double prime does not exist or when f double prime equals 0, because these could be inflection points. And then we look for concave up or concave down, depending on whether f double prime is positive or f double prime is negative. If there is a switch in concavity, then we do have an inflection point. So I want to work through all of this with an example. And the example is given right here. It's f of x is x squared divided by x squared plus 3. And to make this sort of doable, what I've got here is a calculation that's already been done for the first and second derivatives. And so you should try to check these. The first derivative is given right here, and the second derivative is given right here. So when you have a chance, work through and make sure you agree with these formula for the first and second derivative. So to start with, we're going to look at the domain. And the domain is just going to be the entire real line, because we can put any number into f and get a value back. With respect to intercepts, if x is equal to 0, then f of x is equal to 0. So our y-intercept is 0. If f of x is equal to 0, then we have x squared over x squared plus 3 is equal to 0. And that tells us that x squared is equal to 0. So x is equal to 0. And so our x-intercept is also 0. The next thing we want to look at is symmetry. And let's think about f of minus x. That's going to be equal to minus x squared over minus x squared plus 3. And that equals x squared over x squared plus 3, which is equal to f of x. So we have even symmetry. This is not a periodic function. A periodic function would be something, for example, with sines and cosines. And let's look at asymptotes. We'd see a vertical asymptote where the denominator in f would disappear or equal 0. And that's not going to happen because the denominator is always positive. Let's look for horizontal asymptotes. The limit as x goes to infinity, x squared over x squared plus 3, is equal to the limit as x goes to infinity. And now we're going to divide the top and the bottom by the highest power. And so this is going to be equal to the limit as x goes to infinity, 1 over 1 plus 3 over x squared, and that's going to be equal to 1. Okay, so we have a horizontal asymptote as x goes to infinity, that equals 1. And similarly, we can show that the limit as x goes to minus infinity of x squared over x squared plus 3 is equal to 1. Okay, so let's look at the first and second derivative now. The first derivative, f prime of x, is equal to 6x over x squared plus 3 squared. Now we know that x squared plus 3 squared is always going to be greater than 0, so we're really interested in the sign of 6x. And so if we set up our interval, then we can look at the value of 6x and the value of f prime, and then we can decide if it's increasing or decreasing. If we want to look at the critical points, we want to find the points where f prime does not exist or where f prime is equal to 0. So in this case, well, it exists everywhere, okay? But f prime is equal to 0 when x is equal to 0. So that's going to give us a critical number. All right, so we look at the interval minus infinity, 0, and 0, infinity. And so 6x will be negative on minus infinity, 0, and positive on 0, infinity. F prime of x will have the same sign as 6x, so it'll be negative and positive in the same way. And so the function will be decreasing on the interval minus infinity, 0, and increasing on the interval 0, infinity. And so it's going to be like a happy face, decreasing and then increasing. And so by the first derivative test, there will be a minimum at x is equal to 0, and then f of x will also equal 0. Let's look at the second derivative. F double prime of x is equal to 18 into 1 minus x, 1 plus x, over x squared plus 3 cubed. Now x squared plus 3 cubed is always going to be greater than 0. 18 is always going to be greater than 0. And so we're really interested in the sign of 1 minus x and 1 plus x, and so we have to include those in our interval. And so we'll set this up, and we'll have concave up or down. But before we do that, let's work out the inflection points, or the possible locations of inflection points. And so we're looking for points where f double prime does not exist. There's none of those. And points where f double prime is equal to 0. And so f double prime is equal to 0 if x is equal to plus or minus 1. So these are values where we could have inflection points. Okay, so we're going to look at the interval minus infinity, minus 1, minus 1, 1, and 1, infinity. On the interval minus infinity, minus 1, 1 minus x is positive, 1 plus x is negative, and so f double prime of x is negative. This means it's concave down. On minus 1, 1, we have 1 minus x is positive, 1 plus x is positive, f double prime is positive, so it's concave up. On the last interval, 1 infinity, 1 minus x will be negative, 1 plus x will be positive, and so f double prime will be negative, and it's concave down. And so we have inflection points at x is equal to 1, f of x is equal to quarter, and x is equal to minus 1, and f of x is equal to a quarter. Okay, so we've found that we have a function which is decreasing and then increasing, but we have inflection points at plus and minus 1, and so we want to put all of this together and try and graph things out. Okay, now our function f has an intercept at 0, 0, so it's going to go through this point right here. It also has even symmetry, so it's going to, the right-hand side is going to be a mirror of the left-hand side. It has asymptotes that are horizontal, that have a value of 1, and so as x gets large in the positive direction or the negative direction, it's going to approach 1. there are inflection points at 1, 1/4, and at -1, 1/4. And on the interval -1, 1, we have a concave up function, so it looks like a cup opening upwards. And between -infinity and -1 and 1 and infinity, it's going to be concave down. So we'll put all that together. And so we have a function that kind of looks like this. And now we're going to change the concavity. And it's going to look like this. And this side is going to look like this. And so we're reaching these asymptotes at 1 as x goes to plus or minus infinity. We've got the intercept, we've got the evenness, the horizontal asymptotes, decreasing on -infinity, 0, increasing on 0, infinity, concave down on -infinity, -1, and 1, infinity, and concave up on the interval -1, 1. At x is plus or minus 1 and y is equal to 1/4, we have inflection points. So we've got all the different elements in the picture there. And it fits together like a beautiful puzzle. All the pieces have to be consistent with each other. And here you have it.